Hi, I'm Ben-Yaakov. This presentation is entitled Unfolding the Fake Inductor Teaching of Dr. Sobhi Barg. There are some relevant videos of this presentation. Here are the links, and I'm going to print the links on the YouTube video that you are now watching. So let me start with some background. In a series of posts in LinkedIn and some other forums and videos, Dr. Sobhi Barg claimed that the industry is producing fake inductors, that nobody but him understands how to design an inductor with an air-gapped ferrite core, and that for a given B, the volume of the air gap is not proportional to the energy stored in the inductor, and that the result of published papers are incorrect. All of these without any shred of evidence to back it up, and without showing a single example of what is his inductor design method. Now, he promised to do this after repeated requests from me and others, and he promised to do this in a webinar that I attended on February 1, 2023, in vain, because there was no explanation of this supposedly superior design method. It's just more slender, repeating this fake accusation. So what is fake? Well, we know fake is something which is non-genuine, which is counterfeit, and now accusing the industry that they are producing fake inductor is something which is preposterous. I mean, it doesn't make any sense. So I'll give Dr. Barg the benefit of the doubt that what he means perhaps that the industry is not making the best inductor or the optimal inductor. So let's see what he has to say about this in the webinar.
I will just define what is a true and a fake inductor. So, a true inductor is an inductor in which the air gap is designed using the unique air gap equation. A fake inductor is an inductor in which the air gap does not satisfy the unique air gap equation. This is the definition between a true and a fake inductor. Now I will give you an example from industry. What is a fake inductor? Here a table. Usually in industry they sell inductors with same volume, same cross section, same core length, and they get different inductance. So here you can see inductors from different values from 33 micro to 1.5. Same DC resistance, same DC current here, they use RMS current. But these inductors, they have different saturation current. So they have the same DC resistance and same core. So same number of turns. When the inductance decrease, so what is the solution that they are using now? They are only playing on the gap. They are increasing the air gap, so they change the inductance. And that's what you understand from here. Number of turns constant, but air gap, it is changing. That's a fake inductor. The true inductor, with the air gap, when you change, the air gap depends on the number of turns. A change in the number of turns requires a change in the air gap and vice versa. This is what they are doing, a fake inductor. I will not explain in details in what is the fake inductor, but I will give you some advice, and in the future I will go in depth to the fake inductor and explain it.
Okay, so a non-fake inductor is an inductor that is using this unique air gap equation. That's the one. Well, let's have a look at this equation. This term actually is approximately zero, very small, because mu sub r of ferrite is large and L sub c is rather small. So this can be dropped out. And then instead of B max, I can write mu I max n over LC. This is H. This is the magnetic field. H max. And plugging this B max into here, just everything drops, and I'm getting what is very well known, that the equivalent permeability of a gapped inductor is approximately the magnetic path length over the air gap length. So there is nothing special about this unique air gap equation. Now, Looking at it from another point of view, if I write these three equations, mu sub E is LC over LG, B max, by definition the mu times H, magnetic field, and H, Ampere's law, is Ni over LC, then I get this equation. So in any inductor design procedure, at least the one I know of, this will be embedded. This will be part of it, because this is the basic relationship between the magnetic and electrical parameter. So there is nothing special about it. Now I'll show later on that this is supposedly part of the design procedure that Dr. Barg is suggesting, and I'll discuss it later on. Now what about this shameless fake accusation? Dr. Barg brought this table. I don't know from where he got it. There's no reference. This is, by the way, violating basic publication ethics. If you bring something from another source, you have to cite the source. In any event, this is very strange, because it says here the DCR is 1.29 and the current is 30 amp. So we are talking about, what is it, like 1 kilowatt dissipation. So obviously this is milliohm. So let's assume that this is 1.29 milliohm. In any event, this is a very poor example. I'll show later on what I think is a much better example that I'll discuss further. What is showing here is, I guess, a table from some manufacturer. It doesn't say who it is. And this is a core, one core, which is used to produce a number of inductors. And looking at the resistance of the wire, which is about the same, and affects the same current, you can judge that it's the same winding, and the inductances are changed by gap, and consequently, of course, the saturation current will change such that for the high inductance at 33, then you have a smaller gap, and therefore the ferrite core goes into saturation much earlier, only with 2.6 amp. Okay, so what has been done here is that this manufacturer chose one core to produce a number of inductors from the economic point of view, and of course there are some restrictions here. So a customer looking at this picks up the one that it suits its purpose, and if he needs a 33 microhenry with a higher current, he'll go to another set of inductors, another group. So this is not a fake, it is an economical consideration, and I guess what Dr. Barg has in mind, maybe coming from an ivory tower university in Sweden, that for each one of these inductors, the manufacturer should have built, designed, manufactured a core specific to any one of these. This is just childish. I mean, this is not how life is. This is just too costly, and the manufacturer has to bring down the cost, and this he can do if he has the same core, which he is ordering in large quantities, because all of these are using the same core, and then he has another core for another group. So I think the name fake is really not relevant here, and it is a shame that Dr. Barg is using such a expression. But even if he means non-optimal, then he is wrong, because this is optimal design for the manufacturer in terms of the economics, and this is the way to go, and not by some theoretical consideration of the perfect superior core that one can make. This doesn't make sense. So let's have a look now at the family of inductor by worth that makes a variety of inductors. And here is a family actually of high power inductors. As you can see, they are grouped by size, meaning that each side is around one core. and here's the dimension of the core. So you have a number of cores, and around each one there is a number of inductors. So let's have a look at it. Just as an example, here is this group of cores, 2013. Okay, let's have a look at it. There's quite a number of inductors around it, the same core, same size. And then, of course, you can get a number of inductances with this core, between 0.7 microhenry in this case to 22. And then, of course, since this is one core, the saturation current will vary. In this particular case, by the way, we see that the DC is also changing, the RDC, meaning that the windings are also changing. So it's a different approach than the other company. It's a more sophisticated one. Still, obviously, for each one of them, if you would have built a core specific for this particular inductor, it would be, from the theoretical point of view, better. It might be a little bit smaller, but that's not the point. The point is that you have a selection of cores, and a customer needs a inductor. He looks up this specification, he sees whether it suits him. So if a customer is not satisfied with one of these inductors, he'll go to another group and get it. The bottom line is that both this company, I'm sure, knows how to design inductor, at least as Dr. Berg. Well, I would dare to say they know it better, but let's assume that at least as he does. But they are a commercial company who has to make money, so they have to optimize their production, and one way to do this in the case of an inductor is to build groups around certain cores. So to call these inductors fake inductors, it's really a shame. So now, what is the design solution that is proposed by Dr. Barg, at least what he showed in the webinar?
The second equation, it is very famous, and it's called the reluctance model. It is given by this equation. The solution of this system, sorry, I have to change it. Yeah. The solution of this system, it is this, the first solution, it is this equation, which is this one, also equation number one. So here it's something that a bit strange, that the equation number one of the system, it is also a solution of the system. And the second solution for the number of turns, it is given by this equation, and most of the designers, they know it. So here the objective is to solve this system for the number of turns and the air.
Okay, so we have two equations that are supposed to be the key for the design. Okay, one we talked about, and there is another one which is really very basic. But as you can see, this one has an A in it, which means that you have to guess what is the cross-section area of the core before you start the design. This means that this is sort of a iteration type of a design. You guess this, you do a calculation, then you go back, you see if you can get a core with the dimension that you need, and then you go back and forth. I prefer the area product approach. Area product is the area of the winding times the cross-section area of the core. That's the area product. And in the video that I've referenced, there are actually two versions of it. One is the basic one, with the classical one, which you start with the specification of the inductance, I peak, I RMS, B peak, J is the current density of the wire, and K is the packing factor. You start with this, you get an AP, you look up a catalog of cores, and which is giving you a close AP to what you need, and that just about you finish the design. There's another version, in the case it's high frequency, that you have to restrict the magnetic flux density amplitude, and this is just a modified equation. So these equations will lead you to choosing a commercial core, looking up the AP that is usually given in the catalog of manufacturer. Now, I don't know what you do with this, especially that you have to first of all guess what is A. So I don't think that this is a viable approach to do a practical design. And now there is another issue here, which is the relationship between the length of the air gap and the cross-section area. Now, during earlier discussion, Dr. Barg denied the fact that there is any relationship between these. Now he sort of softened out, and so let's see what he has now to say about that.
Equation number 3, it gives you that the number of turns is inversely proportional to the cross-section. From equation number 1 here, so the air gap, it is proportional to the number of turns. So now, if we combine these two results, we will understand that the air gap is inversely proportional to the cross-section. And this is the fundamental mistake that most of the people, they do it. So this is completely wrong approach to understand the relationship between the variables. The problem is it's not the right way to understand it, the relationship between variables. So
what is this relationship of the air gap length and the cross-section area all about? What it is all about? Now, we know, actually it's derived from Maxwell equation, that the magnetic energy density, that is in joule per meter cube, is equal to B squared over 2 mu. This is the well-established electromagnetic fundamental relationship. Now, in the core, we have the ferrite part, and then the energy density is B squared over 2 mu r mu 0. And then we have the air gap, in which the energy density is B squared over 2 mu 0. Now, B is the same thing, and we are here neglecting a fringing effect, another effect. So the energy density, magnetic energy density in the ferrite, since it is divided by mu sub r, is very, very small. So just about all the energy is within the air gap. This is very well known, there's nothing new about that. Now, since this is the magnetic energy density in the gap, and since the volume of the gap is the length times the cross-section area of the core, this is the volume, therefore the product of this volume times the magnetic energy density is equal to the energy stored in the inductor. Again, this is very well known. Now, Dr. Barg, at the beginning, refused to acknowledge that this is correct. And in particular, if you choose a core that has a larger cross-section area, Lg will be smaller because the volume for a given Bn energy has to be the same. Now, this is very important in the magnetic theory because we can get from it important information. For example, if I choose a flat magnetics, which has a relatively large cross-section area as compared, say, to an E-core, then I know that for the given condition of energy and B, then I'm going to need a shorter gap, which is very important in terms of fringing, etc. So this is a very important feature that you cannot just put down and say it's not important and we shouldn't think about it. Well, why shouldn't we think about it? Because this is very important and can teach us a lot about magnetics. But lo and behold, looking at the two equations that Dr. Barg is offering as a design for an inductor, then if you take this first one and you express A, cross-section area, as a function of the other terms, and then you multiply this by this, you get this equation. This by this, you get exactly this equation. So these two equations are actually telling the same story, which is of course fundamental to the electromagnetic theory. And now I'm coming to the effect of DC current bias on ferrite losses, and let's see what Dr. Barg has to say about that.
For high ripple condition, people, they think that Steinmetz equation can work. That's completely wrong also, and this is a big misconception in the literature. Some people have adjusted this one by considering the DC bias effect. That's also a complete misconception in the literature. DC bias has no effect in the core loss, and I will explain this in future meetings.
So he is actually saying that there is no effect of DC bias on the ferrite losses. But there's a lot of evidence, and here I brought a paper by Professor Kollar and co-workers, core losses under DC bias condition based on Steinmetz parameters, in which they're using this Steinmetz model, but that's not the point here. The point is that they've done some measurements on cores under DC bias, DC current bias, and here are some of the results. You see that as the DC magnetic field is increasing, then the losses for a given excitation of magnetic flux density are increasing, okay? Here it is, they're increasing. So how can one say that there is no effect of DC bias current on the losses? So I wonder who is really the faker here. So this brings me to the end of this presentation. I hope you found it of interest. I thank you very much for your attention.